So segment 2 of chapter 10, acids and bases. We were talking about logarithms and how to use our calculator using powers of 10. Again, it's just a shorthand for really big, or in this case, we're looking at really small numbers. Our formula is pH equals negative log of H plus concentration. We had plugged in the 1 times 10 to the negative 7, and it turns out that it's 7. Now, as long as this number right here is a 1, if we take the negative log of any base 10, it's going to be the opposite of whatever that exponent is. So if this was negative 3, so if we did the negative log of 1 times 10 to the negative 3, that would be 3. Okay. Now in an acidic solution, remember H plus is going to go up. So this is why we see our pH actually goes down. So the more H plus that's in solution, the pH goes closer and closer to 0. Okay, so and you can see that here. If we have 10 to the negative 3, we know that 10 to the negative 3 is bigger than 10 to the negative 7. But when we take that negative log, it looks like it's going to be smaller because now it's a 3 instead of a 7. Now, that means your pH then will be smaller than 7. In base then, your pH will be larger than 7. Okay, so if we, again, go back to the equation here and do negative log of 1 times, say, 10 to the negative 12, that'll give us a pH of 12. Larger than 7 means it's going to be a basic solution. We have less H plus there. Now, there's a relationship between H and OH, and that means there's also going to be a relationship between pH and POH. You see, the P just simply means we're taking the log of it. So we can do P of anything at all. Okay, so here we did pH, and now we're going to see POH. And POH is equal to the same mathematical formula, except now we're looking at the OH minus concentration instead of the H plus concentration. Now, if we think back to Kw, the concentration of H plus times the concentration of OH minus, if you remember, was 1 times 10 to the negative 14. That's why Kw had to be a constant. Well, if I take the negative log of both of those, then it turns out that the pH plus the POH is equal to 14. So you have 3 equations now that will help you relate pH to POH, and both of these to the H plus concentration and the OH minus concentration. So you want to get familiar with all 3 of those equations. Again, you won't need to memorize for the exam. You can have a little cheat sheet there with you, little study sheets that you have these equations all ready to go. But you're going to want to have all 3 of those equations at your fingertips when you go to take the exam. All right. Now, if I start plugging in values between 0 and 14, then I come up with the pH scale. 7 is neutral, 0 is acidic, 14 is basic. Now, the relationship between pH and POH is that their sum has to equal 14. That means that the POH scale is literally the reverse of the pH scale. So if my POH is 14, that means it's acidic. Whereas if my POH is 1, that means it's going to be basic. All right, and here you can see that. Remember, they have to sum up. So 0 and 14 would be equal to 14. 7 and 7 would be 14. And then 14 plus 0 would also be 14. That brings us to neutralization reactions. So I'll make sure some practice problems are up for you. That way you can practice pH calculations. pH calculations will be on your exam. Most of them will be 1 times 10 to the something, just that I can see that you have the concept down. But I also want to make sure that you're not stuck always having to have 1 times 10 to the something. So be ready to have your calculator. Make sure you take notes and figure out how your calculator works. Again, whether it's by going back and looking at the last segment or reading the directions for your calculator, the owner's manual, or whether it's getting a hold of me and figuring it out. But either way, you need to see how you can get any number when it comes to the concentrations. That way you can calculate the pH even when it's not 1 times 10 to the something. All right, so neutralization reactions is simply taking that acid and base and watching them produce salt and water. Okay, now we already know that salts are ionic compounds. We've seen those before, it's no big deal. And water here I want to think of as HOH. Now the reason why I want to do that is, remember, we have an acid and a base. Well, if I break this water down, there's the acid and there's the base. So when I take an acid and a base, remember this is going to have an H on it. This has typically got an OH on it. And then I'm going to have a metal here and an anion here. So my metal and my anion will get together to make a salt. And the HOH, of course, comes from the acid and the base itself. So HNO3 plus KOH, HCl plus magnesium hydroxide, sulfuric acid plus sodium hydroxide. Give those a try. So go ahead and pause it here if you want. Write out your answers, see how you do. Let's go ahead and complete and then balance those reactions. All right, so here's your chance to pause. All right, so hopefully you've paused it, you've tried the problems, and now you've hit play, and then you can compare your answers. So the order here is not going to matter. What I'm going to do is I'm going to write the salt first. So I'm going to have K mixing with nitrate, NO3. Potassium is a +1, nitrate's a -1. That means that's going to balance out and equal 0. And of course I'm going to make water, where the H is coming from the acid, and the OH is coming from the base. Now you didn't have to write it this way. You could have written it as H2O, and that would have been fine. Since this is 1-to-1, these are all going to be 1-to-1 as well, and therefore it's already balanced. For our second one, I'm going to do the salt first as well. So we're going to have magnesium. It's a +2. And then we're going to have chloride, which is a -1. So we're going to need 2 of those. And again, we're going to have water, HOH. All right, so right away I can see I have 2 hydroxides, which means I'm going to need 2 waters. That's going to generate 2 H's. So I'm going to put a 2 out in front of the HCl. Let's give me my 2 H's. And now I can see I have 2 chlorides, but that's okay. I needed 2 chlorides for the magnesium anyway. So there we are. 2 in front of HCl, 1 magnesium hydroxide, going to produce 1 magnesium chloride, and 2 waters. Last but not least, sulfuric acid with sodium hydroxide. Again, I'm going to write my salt first. I have Na. I'm going to need 2 of those to go with the SO4. The SO4 is a 2-. And of course, water. Now the acid's going to generate 2 hydrogens, so I know I'm going to need 2 waters. It's going to give me 2 hydroxides, so I'll put a 2 in front of the sodium hydroxide. It's going to give me 2 sodiums, but that's all right. I needed those 2 sodiums anyway. Now, hopefully we did well on that. We were able to complete and balance those with no real issue. In fact, they might have looked very familiar, and that's because it really is just a double replacement reaction. In fact, it should be a little bit easier than double replacement because now you know one of the products has to be water. All right, so the next step then is putting the stoichiometry back into this. So if you're in Chem 100, feel free to stop this now and not have to worry about this too much here. If you're in Chem 110 though, you've got to be ready to do neutralization reactions and come back to stoichiometry. So how many moles of HNO3 are needed to neutralize 0.86 moles of KOH? So again, if you're in Chem 100, you are not responsible for stoichiometry, and so you can actually stop this segment. You're not finished. Make sure you go on to the 3rd segment where we're going to talk a little bit about buffers and possibly some titration leftover pieces there. But again, you don't need to worry about these problems. Chem 110, you might have to go back and reflect on solutions as well as stoichiometry. So here it comes again. So how many moles of HNO3 are needed to neutralize 0.86 moles? So again, we'll need our reaction. So we'll start with HNO3. We're going to mix that with KOH. And that's going to give us potassium nitrate. and water. Now we're going to start with 0.86 moles of KOH. And of course, according to our balanced chemical reaction, that means I'm going to need 0.86 moles of HNO3. Easy peasy lemon squeezy. All right. How many moles of HCl are needed to neutralize 3.5 moles of magnesium hydroxide? And again, these probably feel very familiar, pretty simple. It's just that middle step of our three-step stoichiometric process. However, we have to balance that equation first. So we're going to have HCl plus magnesium hydroxide. And you might want to pause it. Go ahead and work it out yourself. Then come back and check and see how you did. It's going to give us magnesium chloride and a couple of waters, which means I'm going to need a couple of acids. And now I'm going to start with 3.5 moles of magnesium hydroxide. And I want to convert that to HCl. So I'm going to put 2 moles on top, 1 mole on the bottom. And so we get 7.0 moles HCl. All right. So again, that probably felt very familiar to previous chapters. And of course, we don't usually stop at moles. Typically, we're doing these things in solutions. So now we're going to rephrase a little bit. And if it takes 87 milliliters of an HCl solution to neutralize 0.67 moles of magnesium hydroxide, what is the concentration of the HCl? So we have HCl plus magnesium hydroxide. And again, you might want to pause this, go ahead and try to work through the problem, come back to it and see how you did. Excuse me. And of course, we'll make 2 waters. We'll need 2 HCl's. Now, here we're looking for the concentration of the HCl. So we're going to start with 0.67 moles of the magnesium hydroxide. That'll be 1 mole magnesium hydroxide, 2 moles of HCl. And of course, if we're looking for this and we want the concentration, we want the molarity. That's going to be moles per liter. So I actually don't want to cancel the moles out. I'm going to divide this by liters. In this case, I'm going to put a 1 on the top. And I have 87 milliliters, which is going to be the same as 0.087 liters. And I'm going to run that through my calculator. So we have 0.67 times 2 divided by 0.087. That gives me 15.4 molar. And then I'm going to figure out my sig figs here. I only get 2, which means this is going to be 15 molar. And that would be our final answer. All right. Hopefully you figured that out. You did well. If not, go through it again. And of course, we can do another practice problem. If it takes 58 milliliters of an H2SO4 solution to neutralize 0.34 moles of NaOH, what is the concentration? Let's go again. Give it a pause. Go ahead and try to work the problem out, then come back and see how you did. So we're going to take NaOH. We're going to mix that with H2SO4. That's going to give us sodium sulfate and water. We're going to make 2 waters, and we're going to need 2 sodium hydroxides. I'm going to start with 0.34 moles Struggling to write down there. Let's go back up here. So we're going to start with 0.34 moles of NaOH. I want to get rid of that. So for every 2 moles of NaOH, I'm going to need 1 mole of H2SO4. We want to know the concentration of the H2SO4, so I want the moles to go through. I don't want those to cancel out, but I want to know how many milliliters, and I want to convert that to liters. So it's going to be 0.058 liters. All right, final answer then. I'm going to take 0.34, divide by 2, divide by 0.058, and we get 2.9 molar. And that is to 2 sig figs. That will be our final answer. All right, hopefully you got those without too much of an issue there. And at the very worst, if you didn't understand it, it made sense after I went through it. My advice would be to go through it again, try it on your own until you've got it down, and then check out the practice problems as well. All right, the last topic we have then, before we get to buffers, would be titration. Titration is just taking these solutions, using the neutralization reaction to determine an unknown. So basically, when you add the same number of moles of acid and base, the base becomes neutral, right? So the pH will be 7. Now, what we like to do is measure the amount of base we've added. And of course, if we know the concentration of the base, we can use that information to calculate the concentration of the acid. That is a titration. What do the questions look like? If it takes 45 milliliters of a 1 molar NaOH solution to neutralize 57 milliliters of HCl, what is the concentration of the HCl? I know it sounds really complex, but it's actually not too bad. So if it takes 45 milliliters of NaOH to neutralize HCl, then we're going to make sodium chloride and water. And this is going to be 1:1. So that's always the first thing we need is our balanced chemical reaction. So we've got that. Now it says if it takes 45 milliliters of a 1 molar NaOH solution to neutralize 57 milliliters. Well, if we look back at our solutions lab, then we know we have a concentration, we have a volume. These two together will give us moles. If we know the moles of NaOH, then we can use the balanced chemical reaction to get moles of HCl. Once we have the moles of HCl, we know the amount of HCl that was in our sample. That gives us the concentration. So we're going to take 45 milliliters. And we know that's going to be 1 mole per liter. Now I could convert this because right now milliliters and liters won't cancel out, but I'm not going to change that at this point because I know that on the other end of this, I'm going to have molarity again. So that means I'm going to have milliliters again, and I'll be able to get them to cancel out there. Okay, so the next step then will be from our balanced chemical reaction. So at this point, we would be in moles of NaOH. So for every 1 mole of NaOH, it's going to be 1 mole of HCl. And now I'd be in moles of HCl, but I want to be in molarity. And so I'm going to let the 1 go, so that way the moles goes through, it doesn't cancel out. And then I'm going to put that over 57 milliliters. Now this time, I'm going to leave it as 57 milliliters. Again, I want to do that because then milliliters will cancel out with milliliters, and I'll be in liters, which I never converted. Okay, now if you forget and you've converted here, just make sure you convert here as well and go back to liters here. Now I can run this through my calculator. I get 45 times 1 divided by 57, and I get 0.79 with 2 sig figs molar. All right. So hopefully not too bad. Very much just like doing the solution stuff we did in the previous chapter, except now it's a neutralization reaction, and it's going to be an acid and a base. All right. Let's make that go away, and we'll do another practice problem. In fact, I'm going to go ahead and throw two of them up here. And actually, let's go ahead and set this up as extra credit. So you've got two equations here. If it takes 67 milliliters of 0.5 molar H2SO4 to neutralize 15 milliliters of aluminum hydroxide, what was the concentration of the aluminum hydroxide? We'll make that one worth 5 points. Extra credit. How much of a 0.275 molar HCl will be needed to neutralize 25 milliliters of a 0.154 molar NaOH? We'll make that one worth 5 points as well. So just go ahead and work those out on a piece of paper if you want. Snap a picture, email me the pic. Don't forget to put your name on it. All right. Enjoy. That'll be the end of segment 2. And in our last segment, we'll look at buffers. Should be a pretty quick segment. And that will wrap up our chapter for acids, bases, and buffers. All right. Stay tuned for segment 3.